If science ever manages to confirm the existence of cosmic strings, we would be facing one of the most monumental discoveries in history. Not only could they bring us closer to the holy grail of physics, the long-sought theory of everything but in a very distant future, they might even offer us the possibility of time travel, or at least that's what some believe. But could that theory really be true? Welcome to Astroracle, where we explore the vast universe together. The hypotheses predicting their existence describe cosmic strings as filaments thinner than an atomic nucleus. Professor Ken Olam from Tufts University defines them as genuine astronomical tubes, incredibly long. Quote, "Most likely they exist as loops or strings that stretch indefinitely across the universe," he explains. Their size is deceptive, although they are extremely thin. They can concentrate colossal amounts of mass. Olam estimates that a typical loop measuring between 10 and 20 light years in length could contain the mass equivalent to tens of thousands of stars. Over time, however, these loops would shrink, releasing energy in the form of gravitational waves as they travel through the cosmos. In theory, there are two types of cosmic strings, though their behavior would be quite similar. The first type would be cosmic superstrings, predicted by string theory as an yet unproven proposal that claims all matter is made up of tiny, vibrating strings. These superstrings would essentially be the fundamental strings that give rise to everything that exists, but stretched to cosmic scales. The second type would be like a scar from the early universe. In the first moments after the Big Bang, the cosmos was extremely hot and dense, and the four fundamental forces, electromagnetism, gravity, and the strong and weak nuclear forces, may have been unified into one. However, we still know little about the details of such exotic physics. After a brief but dizzying period of inflation, the universe went through phase transitions. These changes of state broke the symmetry of its fundamental forces and gave rise to particles. Princeton University's emeritus professor of astrophysics, J. Richard Gott, compares the phenomenon to the fusion of high-density energy in space. When snow melts, some snowmen may remain intact, he says. Cosmic strings would be those imperfections that survive the change. They can also be thought of as cracks in a block of ice. When you freeze water in an ice tray, bubbles and fissures form. Something similar is believed to have happened when the universe cooled after inflation, leaving behind regions of extremely high density. Although detecting one would be extremely unlikely, encountering a cosmic string could have catastrophic consequences. Imagine one traveling at nearly the speed of light and passing through Earth. It could slice it apart like a ball of clay cut by a wire. According to Cornell University professor David Chernoff, the two halves would most likely slam back together immediately, generating a devastating earthquake. In the best case scenario, it would be equivalent to magnitude 7 quake. In the worst, it could reach magnitude 12.6, far beyond anything ever recorded in history. The search for cosmic strings is already underway. One strategy is to look for ghost copies of the same galaxy caused by gravitational lensing. The enormous mass of these strings would warp space-time, splitting the light that passes nearby. If a string lay between us and a galaxy, we could see two identical images of that galaxy, separated by a small distance. Some cases have looked promising, like in 2003 when a team announced the possible discovery of a cosmic string, though it was later shown that the galaxies in question were different. The problem, explains Olam, is that this method relies on the strings being dense enough to create clear duplications, something now considered less likely. Early models suggested that cosmic strings were extremely massive enough to shape the large-scale structure of the universe, pulling in matter and forming galaxy clusters. But current measurements suggest they are about 10,000 times lighter than originally estimated, too subtle to account for the formation of these structures or to produce obvious double images. Chernoff proposes an alternative method: gravitational microlensing. Instead of observing galaxies, his idea is to monitor the brightness of individual stars. If a string passed in front of a star, the warping of space-time would cause that star's light to suddenly double for a few days before returning to normal. It's a brief but measurable effect. The Veracruz-Rubin Observatory in Chile could be key to the search, as it will continuously observe billions of stars, creating something like a movie of the sky. A microlensing event would not only allow astronomers to pinpoint the string's location, but also direct all available gravitational wave detectors toward that spot. In fact, the gravitational waves may be the best clue yet. In 2023, the Nanograv Observatory reported evidence of a background of long wavelength gravitational waves detected through irregularities in pulsar signals. While the most widely accepted explanation is pairs of supermassive black holes orbiting each other, the pattern matches surprisingly well with what cosmic superstrings would predict. The finding has generated excitement, though Olam remains cautious. They could simply be binary black holes, he warns. More data could confirm or rule out the hypothesis, but that could take years. And still lies ahead the LISA mission, planned for the 2030s, which will be more sensitive to gravitational waves generated by cosmic strings. Confirming their existence would be revolutionary. It would not only strengthen string theory, but also test grand unification theories that describe how the fundamental forces behaved in the earliest moments of the universe. They might even explain puzzling modern phenomena such as the giant black holes the James Webb Space Telescope has detected in the very early universe, possibly seeded by the gravity of string loops. Beyond their scientific value, an inevitable question arises. Could they have practical applications? General relativity allows solutions that involve closed time loops, essentially, traveling to the past. In 1991, Gott discovered that two moving cosmic strings could create a time loop if they were traveling at nearly the speed of light and crossed paths. Theoretically, this would make it possible to go back in time, though it would require extremely improbable conditions. Infinitely long strings moving at 99.99% the speed of light. Gott has explored even bolder ideas, such as manipulating giant loops of string with spacecraft from an advanced civilization to trigger collapses that would create black holes and, with them, temporal shortcuts. But he acknowledges that the energy cost would be staggering. It would require mass equivalent to half a galaxy. On top of that, any traveler would be trapped inside the resulting black hole, with no way to return to tell the tale. Ultimately, what fascinates physicists is not so much the possibility of time travel, but the potential of cosmic strings to reveal fundamental secrets of the universe. They are like fossil remains from an era when the laws of physics were radically different, a direct imprint of the very first instances after the Big Bang. If you're enjoying the video, give it a like, and subscribe to the channel for more content like this. And don't forget to hit the notification bell so YouTube can let you know when we upload a new video. And while the odds of one crossing our path are minimal, it's still unsettling to imagine it. A single filament could slice the Earth in two before we even had time to comprehend what was happening. That's why the real challenge of modern physics is not just to detect them, but to do so before one finds us.